In the vast dark of the cosmos, countless forgotten worlds await. Each tells a story of a forgotten time, orbiting silently in the deep.
Before we go anywhere tonight, I want you to do something small. Look up, not literally, not if you're lying down with your eyes already closed, already halfway somewhere else, but in your mind, look up past the ceiling, past the roof, past the layer of atmosphere that sits above you like a thin blue skin, so thin that if the earth were the size of a basketball, the atmosphere would be no thicker than a coat of varnish. Past that, into the dark, where the stars are, and beyond the stars, much further beyond where the planets are. Not our planets, not the ones with names you learned as a child, arranged in their orderly line from the sun. Other planets, planets around other stars, planets that have never been visited, that may never be visited, that exist in the database of a space telescope as a slight, periodic dimming of distant starlight, the shadow that passes, repeats, passes again, and from that shadow we infer a world, an entire world. From a shadow? Before we begin tonight, tell me something. Tell me what's outside your window right now. Not in detail, just the broad shape of it. City lights or countryside dark, rain or clear. The particular quality of the night where you are. Drop it in the comments before you fall asleep. I'll be reading them in the morning. Now, let's go. What we mean when we say planet, the word is older than the science. The ancient Greeks called them planetae wanderers because they moved against the fixed background of the stars. A small number of lights drifted, night by night, week by week, tracing slow paths across the sky that no star followed. They were wanderers, and for 2,000 years, that was enough of a definition. A planet was a thing that moved against the stars. Mercury moved fastest, completing its loop in a few months. Venus moved with a languid grace that the ancients associated with beauty and desire. Mars moved with a reddish light that the Romans linked to war. Jupiter moved slowly and with enormous dignity. Saturn moved so slowly that a single orbit took nearly 30 years. And those five, Mercury, Venus, Mars, Jupiter, Saturn, were the planets, the wanderers, the moving lights in the sky that separated the known from the mysterious. Then came the telescopes. And Uranus in 1781, Neptune in 1846, and with them the realization that the solar system was larger than anyone had imagined, that there were worlds beyond the reach of the naked eye, worlds that had always been there, always wandering, never seen until we built the instruments to see them. And then in 1992, the first planet outside our solar system, not seen, not photographed, inferred. A slight irregularity in the pulses of a neutron star, a dead stellar remnant spinning in the dark, betraying by the mathematics of its wobble the presence of planets orbiting it. An extraordinary, counterintuitive, deeply strange discovery. The first worlds we found beyond our sun were not orbiting a sun-like star. They were orbiting a corpse. We'll come back to that. But for now, the point is this. In the 30 years since that first discovery, we have found more than 5,000 confirmed exoplanets, worlds around other stars, each one inferred from evidence from the dimming of starlight, from the wobble of the star, from the distortion of light passing through an atmosphere, and each one, if the inference is correct, a real place, a world with a surface, or a world without a surface, a world with an atmosphere, or a world scoured bare, a world where something, not life necessarily, not anything we would recognize, but something happens every day. 5,000 worlds. and the range of them, the extraordinary, rule-breaking, expectation-shattering range of them is what we are here for tonight. The planet where it rains glass. Let me start with one that will stay with you. HD di 1853 Bri. The name is not beautiful. Names in astronomy rarely are. They are catalog designations inherited from the survey that found them, from the instrument that detected them, not chosen for poetry. But the planet itself, the planet is beautiful in the way that something deeply dangerous can be beautiful, in the way a storm is beautiful, seen from a safe distance. HD 189733b is a gas giant, roughly the size of Jupiter, orbiting a star about 63 light-years from Earth. In the constellation Vulpecula, the little fox, which is not one of the famous constellations, not Orion or Cassiopeia or the Southern Cross, a modest corner of the sky that you might look at on a clear night without knowing that 63 light-years away, behind a star you can barely see. There is a world like this. The planet orbits its star so closely that a year on HD 189733b lasts about 2 Earth days. 2 days, the planet and its star are gravitationally locked, like our moon locked to the Earth, always showing the same face. HD 189733b always shows the same face to its star, one hemisphere in permanent day, eternal, scorching, unmerciful day. The other hemisphere in permanent night, the temperature on the day side, over 1,000 degrees Celsius. This is not a planet you could stand on, not even briefly, not even in the most advanced protective suit imaginable. The temperatures alone would be instantly fatal. But that is not the most remarkable thing about HD 189733b. The most remarkable thing is the wind. And what the wind carries, the wind on HD 189733b moves at approximately 8,000 kilometers per hour. 8,000. To put that in perspective, the fastest winds ever recorded on Earth occurred during a typhoon. They reached approximately 380 kilometers per hour. That was considered extreme, record-breaking, terrifying. HD 189733b's winds are 20 times faster. At 8,000 kilometers per hour, the wind would carry anything loose on the surface, if there were a surface, and hurl it around the planet in hours. But there's no solid surface. It's a gas giant. The wind moves through the upper atmosphere, carrying the clouds with it. And the clouds on HD 189733b are not water clouds. They are silicate clouds, silicate particles, the same material that makes glass suspended in the atmosphere. And as these particles are caught in the wind, as they are hurled from the hotter regions toward the cooler regions, they cool, they condense, and they fall. Glass, it rains glass on HD 189733b, sideways, because the wind is moving so fast that anything falling under gravity is immediately overwhelmed by the horizontal velocity. The glass particles fall, but they also move horizontally at 8,000 kilometers per hour. The effective direction of fall is almost perfectly sideways. A rain of glass moving sideways at 8,000 kilometers per hour at temperatures over 1,000 degrees Celsius. This is a real place. This is not science fiction, not the imagination of a writer trying to create an alien world for a novel. This is what scientists have inferred from the light of a star, 63 light-years away, using spectroscopy and the analysis of atmospheric absorption lines. The glass rain is real, and the color of HD 189733b from space, if you could see it, if you were somehow in the right position in the universe to see it, is blue. A deep, vivid, striking cobalt blue, not from water, not from an ocean or an atmosphere like Earth's, from the silicate particles in the atmosphere, scattering blue light in a way that makes the planet look from a distance almost invitingly familiar, almost like Earth, almost like home. And then you get closer, and the glass rain begins. The planet made of diamond, 63 light years away, feels close after where we're going next. 55 Cancri A is 40 light years away. In the constellation Cancer, orbiting a star called 55 Cancri A star slightly smaller and cooler than our Sun. 55 Cancri E is not a gas giant. It's a super Earth, a rocky world, roughly twice the diameter of Earth and about 8 times its mass. In a different solar system with a different orbit, it might be something like a larger, heavier version of the world you're lying on right now. But is orbit. Its orbit is extraordinary. 55 Cancri A completes one full orbit of its star in approximately 18 hours. 18 hours, shorter than an Earth day. The planet is so close to its star that the surface temperature on the day side is estimated at over 2,000 degrees Celsius. The rock on the surface, if there is solid surface at all, is molten. The surface of 55 Cancri is, in all likelihood, a global ocean of lava. But the structure of the planet, what it is made of, when scientists analyzed the density of 55 Cancri E comparing its mass to its volume, they found that the planet is significantly less dense than it would be if it were made of the same materials as Earth, which meant it had to contain significant quantities of lighter materials. Carbon, 55 Cancri E appears to be a carbon-rich world. And in the conditions of extreme pressure that exist inside a planet, the crushing pressure of all that mass bearing down on the core carbon does something extraordinary. It becomes diamond, the mantle of 55 Cancri E. The thick layer between the surface and the core may be composed largely of diamond, a diamond mantle, hundreds of kilometers thick, beneath an ocean of lava, on a planet the size of 2 Earths, orbiting its star every 18 hours. We think about diamonds as precious, as rare, as the hardest natural substance on Earth, formed over millions of years under specific conditions of heat and pressure, found in narrow geological formations, mined with great effort and care. On 55 Cancri, a diamond is structural. Diamond is the mantle, what we treat as a gemstone, something to be cut and polished and placed in a ring and given with great ceremony as a symbol of permanence and love, is on this world 40 light years away, simply the material the planet is made of. The universe does not share our sense of rarity. What is precious to us is abundant elsewhere. What we regard as extraordinary is, in the right conditions, simply ordinary. I think about that sometimes, not just about diamonds, about everything we treat as rare or special or unrepeatable, and what the universe might consider merely the expected result of the right conditions. The darkest world, 3-2b, 750 light years from Earth, in the constellation Draco. 3-2b is a gas giant slightly larger than Jupiter. It orbits its star at roughly the same distance as Mercury orbits our Sun. Close, hot, tidally locked, like HD 189733b, one face always toward the star, one face always in darkness. And 3-2b is dark, extraordinarily, almost unbelievably dark. It reflects less than 1% of the light that falls on it. 1%. For comparison, Earth reflects about 30% of the light that hits it. The moon reflects about 12%. Even a piece of black coal reflects about 4%. 3, 2b reflects less than 1%. It is darker than coal, darker than black paint, darker than almost any substance we have in our everyday experience. If you held a piece of trash, 2b's atmosphere in your hand, if such a thing were possible, it would appear almost perfectly black, not dark blue or dark gray or the deep charcoal black of a blackboard. Black in the way that an object becomes black when it absorbs essentially all the light that touches it. We don't know exactly why. That is the honest answer. We have hypotheses. The atmosphere may contain light-absorbing chemicals, sodium, potassium, titanium oxide that absorb incoming radiation across a wide range of wavelengths. The extreme temperatures may destroy any reflective clouds that might otherwise form. The specific chemistry of the atmosphere may conspire in ways we don't fully understand to create a world that simply swallows light. But the result is a planet so dark that if it weren't slightly warmer than the surrounding space, warm enough to emit a faint reddish glow from its own heat, it would be essentially invisible. A dark world, moving through the dark, nearly indistinguishable from the darkness around it, and yet real, massive, hot, profound, just dark. There is something about this that I keep returning to. The idea of a world that absorbs everything, that takes in all the light that falls on it and gives almost nothing back. Not malevolent, not intentionally dark, just constituted that way. Made of materials that happen to absorb rather than reflect. A world that is there, fully, completely there, but that reveals almost nothing of itself. How many things are like that? How many things exist in our lives in the universe that are fully real, fully present, fully massive and consequential, and yet reveal almost nothing of themselves to anyone looking? Tres, 2b, is one of the universe's quiet things. Dark and real and moving through the dark, the world with two suns. You have seen the image, even if you have never watched the film. The image has passed into the visual vocabulary of our culture so completely that most people recognize it immediately. A figure standing on a desert planet, two suns setting on the horizon, twin points of light, warm and amber, sinking behind a landscape of dunes and rock. George Lucas put that image in Star Wars in 1977. And for 30 years, it was science fiction. A beautiful image, an iconic image, an image that suggested the alienness of another world in a way that was immediately, viscerally comprehensible. And then, in 2011, NASA announced the discovery of Kepler 16b, a planet orbiting two stars. A real one, Kepler 16b, is roughly the size of Saturn, a gas giant, not a rocky world. You couldn't stand on it and watch the double sunset the way Luke Skywalker does in Star Wars. But it orbits two stars, a larger orange star and a smaller red star that orbit each other. And from the perspective of Kepler 16b, there are two suns in the sky. Or rather, the appearance of two suns depends on where the planet is in its orbit. Sometimes both stars are visible simultaneously. Sometimes one is behind the other. Sometimes you would see one bright point and one dim point. Sometimes a single merged light. The sky on Kepler 16b or above Kepler 16b, since there's no solid surface to stand on, is never the same twice. The light changes constantly as the two stars move relative to each other and relative to the planet. A sky in motion, always different, always rearranging itself. In the 30 years since exoplanet discovery began, we have found many circumbinary planets, planets that orbit two stars. Kepler 16b was among the first confirmed examples. But it is not alone. The universe, it turns out, has no particular preference for single-star solar systems. Roughly half of all Sun-like stars are in binary or multiple star systems, which means roughly half of all planetary systems, if they exist, orbit not one star but two or more. The double sunset is not exotic. It may be the norm. Our own single-star solar system, the clean, orderly, one-sun system that gave us a single point of light in the sky, a simple day-night cycle, a stable climate regime may be the unusual case. The universe's standard planetary experience may involve a more complicated sky. More light, more variation, more complexity, more beauty, perhaps, certainly more strangeness. Planets around a dead star. Now, here is the discovery that I think about most. The one that, when I first really absorbed it, made me sit quietly for a moment. The first exoplanets ever confirmed, not around a sun-like star, around the pulsar Pser B1257+12. A pulsar is a neutron star, the collapsed core of a massive star that ended its life in a supernova explosion. When a star much larger than our sun runs out of fuel, it collapses in a fraction of a second from a sphere perhaps 1,000,000 kilometers across to a sphere perhaps 20 kilometers across. The density at which that collapse stops when the neutrons packed into the core push back hard enough to prevent further collapse is almost beyond imagination. A teaspoon of neutron star material would weigh approximately 4 billion tons, and the neutron star spins, conservation of angular momentum, the same physics that makes the spinning ice skater speed up when she pulls in her arms, takes the original slow rotation of the giant star and amplifies it as the collapsing core shrinks into a rotation rate of hundreds of times per second. The pulsar PSR B1257 plus 12 spins 161 times per second. It emits beams of radio waves from its magnetic poles. And because it spins, those beams sweep across the sky like a lighthouse, a pulse, precisely timed, arriving at Earth 161 times every second. And in 1992, Alexander Wolszczan and Del Frel were studying the timing of those pulses. The pulses were not perfectly regular. There were tiny, systematic variations. The pulses arrived slightly earlier than predicted, then slightly later, then slightly earlier again. The mathematics of those variations pointed to one explanation. Something was orbiting the pulsar. Multiple somethings, planets, 2 planets, it turned out initially. Later, a third was found, orbiting a stellar remnant, orbiting the dead core of a star that had, at some point in the past, exploded with a violence that would have destroyed any planets that existed before the explosion. These planets formed after the supernova, from the debris of the explosion, from whatever material was left orbiting the pulsar after the star died. New worlds built from the ruins of a dead star, orbiting a lighthouse of radio waves, spinning 161 times per second in the dark. I don't know what to do with this entirely. The philosophical weight of it, that the death of a star does not end the possibility of worlds, that from destruction, from the most violent event in the universe, short of the Big Bang itself, from the collapse and explosion of a star, new planets can form, new worlds, not thriving worlds, probably, not worlds where anything lives or could live. The radiation environment around a pulsar is lethal. The planets of PSR B1257 plus 12 are almost certainly sterile, but they are there, real, orbiting, built from the ashes of a star. The universe does not waste material, the planet being eaten alive. WASP 12b, 1,000 light years away, also a gas giant, also tidally locked, also orbiting its star at an insane proximity, completing one orbit every 26 hours. But WASP 12b has a particular distinction. It is being consumed. The gravitational field of its star is so intense at the distance at which WASP 12b orbits that it is pulling material away from the planet's atmosphere, tearing it loose, drawing it into a stream of gas that spirals down into the star. The planet is losing mass. Millions of tons of atmosphere per second, being stripped away by the gravity of the star it orbits too closely. WASP 12b is not spherical. The gravitational pull of the star distorts it, stretching it slightly toward the star like a water balloon being pulled from one side. It is an egg-shaped planet, a planet being deformed by the forces acting on it, and it is shrinking at its current rate of mass loss. WASP 12b has perhaps 10 million years before it is entirely consumed. 10 million years sounds like a long time. In human terms, it is incomprehensible. 10 million years ago, our ancestors were small apes in Africa, perhaps 3 feet tall, with brains considerably smaller than ours. But in cosmic terms, 10 million years is brief. The universe is nearly 14 billion years old. 10 million years is less than 0.1% of the age of the universe. WASP 12b is by cosmic standards in the final moments of its existence, being slowly, continuously, unstoppably consumed by its own star. There is something in this that speaks to a kind of cosmic impermanence, that even planets, things we think of as permanent, geological, solid, lasting, can have endings, can be consumed, can be drawn into the thing that both sustains them and destroys them. The star gives the planet its orbit, its warmth, its reason for being where it is, and the star takes the planet apart, particle by particle, year by year, in the long, slow, inevitable gravity of proximity. The water world, Geye Ezerketzastizanej, 42 light years away, a super-Earth, about 2.5 times the diameter of Earth, and GJ 1214b appears to be covered in water. Not like Earth, where oceans cover about 70% of the surface and land breaks through in continents and islands. GJ 1214b appears to be a world where water dominates entirely, but not the water we know. The conditions on GJ 1214b, the pressure and temperature at depth would produce forms of water that don't exist naturally on Earth. Hot ice, superionic water, in which the oxygen atoms form a crystal lattice while the hydrogen ions flow freely through it like a liquid within a solid. Water in phases that have no names in everyday language because they have never been needed. The ocean of GJ 1214b, if it is an ocean, is not the Atlantic or the Pacific. It is something for which we don't have the right words. Something that behaves like water, that is made of water molecules, but that exists in a state that we have only ever created briefly in laboratory conditions at extreme pressures, and then only for fractions of a second. On GJ 1214b, if the models are right, those states exist stably, permanently, across an entire planetary surface for billions of years. I find something quietly beautiful about this. The idea that water, the substance most associated with life as we know it, the molecule that makes up most of your body, the thing that falls from the sky and fills the rivers and makes the planet from space look blue and alive, can exist in forms so extreme, so alien, so far from the cup of water on your bedside table that they require new physics to describe. Water is not one thing. Water is a word we use for a molecule, H2O, that can take forms ranging from the ice in the freezer to the steam above a kettle to the suprionic crystal of a deep planetary interior. The familiar and the alien, the same molecule, different conditions, different worlds, the planets we haven't found yet. 5,000 confirmed exoplanets. It sounds like a large number, but consider this. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. If even a fraction of those stars have planets, and the evidence strongly suggests that planets are the rule, not the exception, that most stars have planets, then the number of planets in our galaxy alone is in the hundreds of billions. Possibly more planets than stars, possibly far more. We have confirmed 5,000. We have detected, but not yet confirmed, thousands more. But the vast majority of the planets in our galaxy have never been detected, have never produced a slight dimming of a star that we happen to be watching, have never caused a detectable wobble in the star's position, are simply out there, unknown, undetected, each one a world, some of them perhaps not unlike Earth, rocky, in the habitable zone, with liquid water, with atmospheres, some of them perhaps like nothing we have imagined. Stranger than HD 189733b, stranger than 55 Cancri, stranger than anything in our catalog, because the 5,000 we have found are, in a sense, the easy ones, the ones close enough to detect, the ones big enough to cause a measurable dimming, the ones in the right orientation relative to Earth for the transit method to work. The others, the smaller ones, the more distant ones, the ones in orbital planes that don't align conveniently with our line of sight, are still out there, waiting, not for us specifically, just existing as they have existed for as long as their stars have burned, what these worlds tell us. I want to say something about what we do with all of this. Not scientifically, not what the data means for our models of planetary formation, but personally. What do you do with the knowledge that the universe contains worlds made of diamond, and worlds where it rains glass, and worlds that orbit dead stars, and worlds being slowly eaten by their own suns? I think, and this is personal, this is my own response, not a scientific conclusion, I think it changes the texture of the night sky, which can feel empty and cold and indifferent, becomes something different when you know what is behind it. Not empty, full, incomprehensibly full of worlds, each one real, each one subject to its own physics, its own chemistry, its own history of formation and change, and whatever processes unfold on its surface or in its atmosphere. None of them aware of us, none of them caring, but none of them empty either. And there is something in that, in the fullness of it, that I find genuinely comforting. Not because any of those worlds could help us or sustain us or even be reached, but because the universe that contains them is clearly not a universe that is stingy with worlds. It is not a universe that makes one planet and calls it done. It makes planets abundantly, extravagantly, in every configuration the physics allows, around every kind of star, in every kind of orbit, of every size and composition and temperature. A universe so prolific with worlds, that we are only just beginning to count them. And everyone we find is stranger than we expected, and more beautiful and more real. The darkness between, let me take you somewhere before we sleep, between the planets, not on a planet, not in an atmosphere, not on the surface, between the interplanetary space, the void that separates world from world. It is not actually empty. The space between planets is filled with the solar wind, a constant stream of charged particles flowing outward from the sun at speeds of 400 to 800 kilometers per second, invisible, undetectable without instruments, but present, and it is filled with dust, microscopic particles of rock and metal and organic compounds left over from the formation of the solar system, drifting, moving in their own slow orbits. And it is filled with light. Not just the light of our sun, but the light of every star in the galaxy and the light of every galaxy beyond. A background radiation of photons from every direction. Most of them too faint to see, but real, present. The space between worlds is not nothing. It is a medium, a thin, sparse, almost nothing medium, but structured with history, with physics, with the residue of 4.5 billion years of solar system evolution. And in the exoplanetary systems, we have found the space between their worlds is also filled, also structured, also carrying the evidence of their histories. 40 light years away in the GJ 1214 system, the space between GJ 1214b and its star is not empty. It is thin, but it is there. The same kind of not nothing. That exists here, the scale of it all. I want to do something that might be uncomfortable. I want to ask you to feel the scale, not intellectually, not as a fact to be filed away, as something felt. 40 light years. Light travels at approximately 300,000 kilometers per second. In 1 second, light crosses a distance equal to 7.5 times the circumference of the Earth. In 8 minutes, light travels from the sun to the Earth. In 40 years, light travels 40 light years. The light that left GJ 1214, the star that GJ 1214b orbits 40 years ago, is arriving at Earth right now. If GJ 1214b has an atmosphere that absorbs and re-emits light, which it does, and we have studied that light, then the light we have analyzed from its atmosphere left that atmosphere 40 years ago. When that light left GJ 1214b, it was 1985. You may have been a child, or not yet born, or already an adult in a world with no internet, no smartphones, no widespread knowledge of exoplanets, and the light was traveling, already on its way, from a water world 40 light years away to a telescope on Earth, to the spectrum that told us what it was. We are not receiving transmissions from the present. We are receiving letters from the past. Every star we look at, every planet we infer, is a message from a time before the observation. The universe we study is the universe as it was, never the universe as it is. Right now, in the actual present, the universe is unknowable in its present state. Only its past reaches us. The last planet, I want to end with one more world. Not the strangest, not the most dramatic, the most recent. In 2022, the James Webb Space Telescope turned its mirrors, its 18 gold-coated hexagonal mirrors, each one polished to a precision of nanometers, toward WASP 39b, a hot gas giant. not unlike HD 189733b, about 700 light years away. Not exotic by the standards of what we have discussed tonight, but Webb looked at its atmosphere, and for the first time in history, we detected carbon dioxide in the atmosphere of an exoplanet. Carbon dioxide, CO2, the same molecule that you exhale right now with every breath, the same molecule that trees absorb in the process of photosynthesis, the same molecule that is warming our atmosphere and changing our climate, that molecule in the atmosphere of a planet 700 light years away. It sounds modest after diamond mantles and glass rain and pulsar planets, but what it means is extraordinary. It means we can read atmospheres. We can take the light that passes through a planetary atmosphere as the planet transits its star, and we can analyze it. And we can tell you what molecules are in that atmosphere. Not just CO2, anything that leaves a spectroscopic fingerprint, water, methane, oxygen, ozone, the molecules of life, if they are there, if some planet somewhere in our observational range has an atmosphere rich in the chemical signatures of life, the specific out of equilibrium mix of gases that only biology produces, we will, in principle, be able to see it. Not visit it, not confirm life directly, but see the chemical suggestion of it, the atmospheric whisper of something alive. We are building the instruments. We are developing the techniques. We are learning to read the light, and the universe, with its 5,000 confirmed worlds and its hundreds of billions of unconfirmed ones, is waiting, drifting towards sleep. The glass rain is falling on HD 189733b right now, sideways, at 8,000 kilometers per hour, on a planet that has never known anything else. The diamond mantle of 55 Cancri E is pressing down on its molten core right now, has been pressing down for billions of years, will continue pressing long after everything we have built is turned to dust. The pulsar PSR B1257 plus 12 is spinning right now, 161 times per second. Its planets orbiting in silence around it, the remnants of a supernova, shaped into worlds by the same physics that shaped ours. And somewhere in the space between here and the edge of what our telescopes can reach, there are worlds we haven't found yet. Worlds stranger than anything we have imagined. Worlds that follow rules we haven't written yet. Worlds that would, if we could see them, change everything we think we know about what a planet can be. They are out there right now. As you breathe, as the night deepens around you, as your thoughts slow and soften and begin to dissolve into the particular quiet of sleep, the universe is full. Impossibly, extravagantly, beautifully full of worlds, and you are on one of them. On a small, rocky, water-covered, atmosphere-wrapped world, orbiting one star, in one solar system, in one galaxy, among hundreds of billions. And you are aware of all of it, or some of it, enough of it. Let that be enough. Let the glass rain fall. Let the diamond mantle press. Let the pulsar spin. Let the dark planet move through its dark orbit, and let yourself move towards sleep, gently, the way the light moves through space, without hurry, without destination, just traveling in the direction it's going until it arrives. Wherever it arrives, sleep now. The weird planets will be there in the morning. They always are, moving through their orbits, obeying their physics, real and strange, and quietly magnificent. In the dark between the stars, There is a moment in every scientific discipline when the model breaks, when the data comes back and it doesn't match what the theory predicted. And the scientists look at each other and someone says quietly, that shouldn't be there. That's not how this works. And the room gets a particular kind of still. The still of a field being rewritten. Planetary science has had many such moments. But the era of exoplanet discovery has produced more of them in a shorter time than almost any other period in the history of astronomy, because we built our models of what a solar system looks like based on one solar system. We had one example, one data point, and from that data point, we built a comprehensive theory of how planets form, how they migrate, where they end up, what sizes they are, what they are made of, a theory of remarkable sophistication and internal consistency. That turned out to be wrong, not entirely wrong, not wrong about the physics. The physics is right, but wrong about what the physics produces, what it can produce, what it apparently regularly produces in the vast variety of planetary systems that we have been finding since 1995. The first exoplanet discovered around a sun-like star was Lima plus Satu Pegasi b, found by Michel Mayor and Didier Queloz in 1995 using the radial velocity method. The wobble of the star caused by the gravitational pull of an orbiting planet, and what they found was impossible, or should have been impossible. According to the models, Lima plus Satu Pegasi b was a gas giant, roughly half the mass of Jupiter. So far so good. Gas géant exist. Jupiter is a gas giant. We understand gas giants. But 51 Pegasi b was not where Jupiter is. It was not in the outer solar system, where gas giants form. According to the model, where the temperature is low enough for the volatile compounds, the ices, the water and ammonia and methane that gas giants are built from, to condenser, to provide the solid core around which the gas accumulates. Lima plus Satu Pegasi b was orbiting its star at a distance of approximately 4 million kilometers. Jupiter orbits our Sun at approximately 778 million kilometers. 51 Pegasi b was 200 times closer to its star than Jupiter is to the Sun, and it completed one orbit every 4¼ days. 4¼ days. A year that fits inside a week. This should not exist. According to the models, a gas giant cannot form that close to a star. The conditions are wrong. The temperature is too high. The volatile compounds evaporate before they can condense, before they can form the solid core. That gas giant formation requires a gas giant that close to a star should not be there. And yet, there it was. In the data, unmistakable, a planet that broke the rules. On the very first day, we now know what happened. 51 Pegasi b didn't form there. It formed further out in the cold outer regions of its solar system, where the conditions were right. And then it migrated, moved inward, pushed by interactions with the disk of gas and dust that surrounded the young star. In the early solar system, the disk exerted a drag on the forming planet, slowing its orbit, causing it to spiral inward toward the star, until the disk dissipated and the migration stopped, and the planet was left where it is now, far inside the orbit, where it formed. This process, planet migration, is now understood to be common, perhaps universal, perhaps something that happens in every solar system. To some degree, our own solar system went through it. Jupiter migrated inward, then back out in what is sometimes called the grand tack, a migration that fundamentally shaped the architecture of our solar system, the size of the asteroid belt, the small size of Mars, perhaps even the existence of the conditions that allowed Earth to form as it did. The hot Jupiters, the class of planets that 51 Pegasi b inaugurated, are still among the most studied objects in exoplanet science. Not because they are the most common. They are not. We found them first because they are the easiest to find. Large planets close to their stars produce large signals, both in the radial velocity method and in the transit method. They are overrepresented in our catalogs relative to their actual frequency, but they are extraordinary objects. Regardless, imagine standing on the surface of a hot Jupiter. They have no solid surface. They are gas, all the way down, or nearly all the way, until the pressure becomes so extreme that the gas behaves like a liquid, and deeper still, like a metal. Metallic hydrogen, a state of matter that exists only under the crushing pressures of planetary interiors, a state of matter that we have created briefly in laboratory explosions, and that exists stably in the cores of giant planets. Imagine instead floating in the upper atmosphere of a hot Jupiter, the sky above you, not blue, not black, but a deep, ambiguous color determined by whatever molecules happen to dominate the atmosphere. Orange, perhaps, from titanium oxide, or a deep rust brown from iron vapor, or the vivid blue of HD 189733b from silicate haze. The sky is not empty. It is full of cloud, but not the white, fluffy clouds of Earth. Clouds of mineral particles, iron droplets, silicate dust, clouds that would damage anything that flew through them, as surely as flying through a sandstorm. The wind on the day side, the temperature gradient between the perpetually illuminated hemisphere and the perpetually dark hemisphere drives winds of extraordinary violence. Thousands of kilometers per hour, the fastest sustained winds in the known universe, not gusts, sustained, year-round, for billions of years. Winds that carry the mineral clouds from the hot side to the cold side, where the minerals cool and condense and fall as rain, not water rain, iron rain, silicate rain, glass rain, the various hot Jupiters in various states of chemistry, each one raining something different, something extraordinary. Rogue planets, the worlds with no star. Now let me tell you about the loneliest worlds in the universe. The rogue planets, planets with no star, planets that drift through the galaxy in complete darkness, warmed by nothing, orbiting nothing, belonging to nothing, alone in the vast cold between the stars. Rogue planets form in two ways. Some form in solar systems and are then ejected by gravitational interactions with other planets, the same kind of gravitational dynamics that caused Jupiter to migrate that shaped our solar system can also fling planets out of their solar systems entirely. If the gravitational interaction is strong enough, if the planet is in the wrong place at the wrong time, the planet accelerates, gains energy from the interaction, exceeds the escape velocity of the system, and leaves, never to return, thrown out into the dark. Some rogue planets may form in the interstellar medium itself, from collapsing clouds of gas and dust, too small to ignite nuclear fusion, too small to become stars, but large enough to form planets, free-floating planetary mass objects that formed in isolation, that have never orbited a star, that have always been in the dark. The number of rogue planets in our galaxy is uncertain, but estimates suggest that they may outnumber conventional planets orbiting stars by a significant margin. Some estimates suggest there may be more rogue planets in the Milky Way than stars. If this is correct, then the most common planetary experience in our galaxy is not the experience of orbiting a star. It is the experience of drifting in the dark between the stars, alone, cold, without a sun. The planets we know, the ones that orbit stars, may be the minority, the unusual ones, the ones with the luxurious experience of warmth and light. The surface of a rogue planet is cold, colder than anything on Earth, colder than the poles in winter, colder than the top of Everest in a blizzard. Depending on the size and composition of the planet, the surface might be at temperatures approaching absolute zero, the lowest possible temperature, the point at which molecular motion essentially stops. There is no sunlight, no radiation falling from a nearby star, no warmth from outside, only the residual heat from the planet's formation, from the gravitational energy that was converted to heat when the planet assembled, from the radioactive decay of elements in the rock, the internal heat of a cooling planet leaking slowly outward through the rock. And for some large rogue planets, this internal heat may be enough to maintain liquid water under an ice shell in subsurface oceans kept liquid by geothermal heat, the way Europa's ocean is kept liquid by the tidal heating of Jupiter's gravity, the way Enceladus spurts its subsurface ocean into space through cracks in its ice shell. A rogue planet, drifting in the dark, far from any star, might harbor under its ice liquid water, warmed by its own interior, in the absence of sunlight, in complete isolation from the rest of the universe. A subsurface ocean, alone in the dark, between the stars. I find something both desolate and beautiful about this. The desolate part is obvious. A world with no sun, no light, no warmth from outside, just the cold and the dark and the vast distance to the nearest star. But the beautiful part, the remarkable part, is that even there, even in the most isolated, most lightless, most apparently inhospitable circumstance, the conditions for liquid water may persist. Life, as far as we know, requires liquid water, and liquid water may exist on rogue planets. In the interstellar dark, without any star, without any sunlight, just the internal heat of a cooling world pressing up against the ice, keeping it liquid in the darkness beneath. if life can arise in that darkness, if the chemistry works in the isolated ocean of a rogue planet drifting between the stars, then life is not dependent on stars, not dependent on sunlight, not dependent on the warming of a distant nuclear furnace. Life could be fundamentally different from what we assume the super Earths, worlds that dwarf ours, and defy categorization when astronomers first began finding exoplanets. They expected to find worlds like those in our solar system, rocky planets close to the star, gas giants far out. That is what our solar system has. That is the template, the pattern we expected the universe to repeat. Instead, the most common type of planet in our galaxy appears to be something that our solar system doesn't have at all. Super Earths, planets with masses between roughly 1 and 10 times that of Earth, larger than Earth, much smaller than Neptune, in a size range that our solar system simply skipped. We have no local example, no planet in our solar system with a mass of 3 or 4 or 5 times Earth. We have Earth at 1 Earth mass, and then we have Neptune at 17 Earth masses, a gap with nothing in it. But in planetary systems around other stars, that gap is filled. Super Earths are everywhere. They appear to be the most abundant planetary type in the galaxy, and we don't have one. We don't have any local example to study up close, to understand from the inside. The most common kind of planet is the kind we cannot visit, cannot see in detail, cannot fully understand, because we have no nearby representative. What is a super Earth like? We genuinely don't know. In detail, the models make predictions, but the models are uncertain in ways that matter. At the low end of the mass range, a super Earth might be a rocky world, like Earth, but larger, with stronger gravity, a deeper atmosphere, perhaps a larger ocean, perhaps more tectonic activity from the more energetic interior. These worlds might be, in many ways, better suited for life than Earth. Larger surface area, more geological activity, producing more nutrients, stronger magnetic field, perhaps protecting the surface from radiation for longer than Earth's magnetic field lasts. These worlds are sometimes called superhabitable, a term coined by the astrobiologist René Heller to describe worlds that might be more hospitable to life than Earth itself. In certain respects, at the high end of the mass range, the picture changes. A super Earth of 8 or 9 Earth masses may have accumulated enough gravity during its formation to capture a significant hydrogen atmosphere, to begin the transition from a rocky world to our mini Neptune, a world dominated not by rock and ocean, but by a deep atmosphere of hydrogen and helium with perhaps a super hot, super pressurized water layer beneath. These worlds are sometimes called water worlds or ocean worlds, or mini Neptune, depending on which features the models emphasize. The terminology is unsettled because the worlds themselves are unsettled. In our understanding, we are looking at them from light years away, reading their atmospheric spectra, inferring their densities, building models, and then arguing about what those models mean, about whether they are right, about what these worlds really are, in the way that all science is arguing productively toward a better answer. Kepler 442 is sometimes cited as one of the most Earth-like exoplanets yet found, located about 1,200 light-years away. In the constellation Lyra, it is a super-Earth, about 1.3 times the radius of Earth, orbiting a star slightly cooler than the Sun. At the distance, that places it comfortably in the habitable zone, the region around the star where the temperature is right for liquid water on the surface. Not too hot, not too cold. Kepler 442b receives about 70% of the solar flux that Earth receives from the Sun. Slightly less light, slightly cooler, but within the range that models suggest could support liquid water, could support a stable climate, could support, in principle, the conditions for life. We cannot see the surface. We cannot detect an atmosphere. We cannot know with any confidence whether Kepler 442b is a rocky world with oceans and clouds and a biosphere, or a featureless, airless, geologically dead rock. We see a shadow in the light of a star 1,200 light-years away. And from that shadow, we infer a world, and we wonder the planets around red dwarfs, the most common stars, and the worlds around them. 70% of all stars in the Milky Way are red dwarfs, M-type stars, small, cool, dim, burning their fuel so slowly that they will last for trillions of years, long after the Sun has died and the Earth has been swallowed and the universe has entered a different, quieter phase. The red dwarfs will still be burning, and most of the planets in the galaxy, the majority, orbit red dwarfs. This is important because for a long time, red dwarfs were considered poor candidates for hosting habitable planets. The habitable zone around a red dwarf is much closer to the star than the habitable zone around a sun-like star because the star is dimmer. The planet must orbit closer to receive enough warmth for liquid water, and at that close distance, the planet is likely tidally locked, always showing the same face, one side in permanent day, one side in permanent night. This was considered a problem. A planet with one side in a permanent blazing noon and the other side in permanent freezing darkness seemed unlikely to have the stable, temperate climate across most of its surface that life seems to require, at least life as we know it. But the models have evolved. More sophisticated climate simulations have shown that a tidally locked planet is not necessarily uniformly hostile. The day-night temperature gradient drives atmospheric circulation, moving heat from the hot side to the cold side, potentially moderating the extremes, creating a habitable band around the terminator, the boundary between day and night, where the temperature might be, neither too hot nor too cold, where liquid water might exist, where an atmosphere dense enough might buffer the temperature swings and create a narrow zone of something like temperate conditions, perpetual dawn, or perpetual dusk, depending on where you stand, with the sun always on the horizon, never rising, never setting, a sky that never changes. The star Trappist, one is a red dwarf, about 40 light years away from Earth. In the constellation Aquarius, Trappistux is so small and so dim that despite being only 40 light years away, it is invisible to the naked eye. You cannot see it from where you are lying right now without a telescope. And yet, around this invisible, unremarkable, small and dim red dwarf, 7 planets orbit, 7, all of them roughly Earth-sized, all of them in or near the habitable zone, 3 of them in the most optimistic habitable zone estimates, TRAPPIST, INE, NF, and ICHI, 3 Earth-sized worlds in the habitable zone of a star 40 light years away. This discovery, more than 2017, using the TRAPPIST telescope in Chile, and subsequently confirmed and expanded by Spitzer and Kepler and Hubble, changed the conversation about the frequency of potentially habitable worlds. If a single red dwarf 40 light years away can host 3 potentially habitable planets, then the number of potentially habitable worlds in the Milky Way is not hundreds or thousands. It is billions, tens of billions, perhaps more. We have looked at the TRAPPIST-1 planets with the James Webb Space Telescope. TRAPPIST, the 1b, the innermost planet, was studied first. And the results were mixed in the sense that they were informative, but not in the way that the hopeful headlines predicted. TRAPPIST 1b appears to lack a substantial atmosphere. The infrared emission from the planet is consistent with a bare rock with no atmosphere to retain heat or to moderate temperatures. This is a concern not just for TRAPPIST 1b, but for the habitable zone planets further out, because red dwarfs are not quiet stars. They are active. They flare. They emit intense bursts of ultraviolet and X-ray radiation that can strip atmospheres from nearby planets if those planets lack strong magnetic fields. To protect them, whether the TRAPPIST-1 planets have magnetic fields strong enough to protect their atmospheres is not yet known. We are looking, we are building the instruments, we are developing the techniques. The answer is coming. We just don't have it yet. The atmospheres, the thin envelopes that make everything possible. An atmosphere is a thin thing, embarrassingly thin. When you look at Earth from space, the atmosphere is a delicate blue haze at the edge of the planet, a layer so thin relative to the size of the Earth that if the planet were the size of a basketball, the atmosphere would be the thickness of a coat of varnish. Less than that, and yet everything lives in it. Everything depends on it. The atmosphere is the most important thing about a planet from the perspective of life. It regulates temperature. It provides the gases that biochemistry requires. It protects from the radiation of space. It distributes water in the form of rain and snow. It carries sound, makes weather, gives the sky its color, makes sunsets beautiful, makes life possible. A planet without an atmosphere is a planet without biology, or so we believe, based on what we know, which is based on one example. The chemistry of an atmosphere encodes the history of the planet. Earth's atmosphere is not what it started as. The young Earth had a thick hydrogen and helium atmosphere from the solar nebula that it was assembled from that atmosphere was lost, blown away by the young sun's solar wind. The second atmosphere, built from volcanic outgassing, was primarily nitrogen, carbon dioxide, and water vapor, no oxygen, not yet. The oxygen came later from the cyanobacteria, the photosynthetic microorganisms that learned to split water and release oxygen as a byproduct. Oxygen, which is chemically reactive, dangerous, toxic to many early organisms. The Great Oxidation Event, 2.5 billion years ago, when oxygen began to accumulate in the atmosphere, was a catastrophe for the organisms that had evolved in its absence, a mass extinction caused not by an asteroid or a volcanic eruption or climate shift, but by the biochemical success of cyanobacteria, the most consequential pollution event in the history of the planet that also made possible everything that followed, every complex organism, every animal, every plant, every creature that has ever drawn a breath, including you. What would the atmosphere of an inhabited exoplanet look like? From a distance, from the spectroscopic signature of its starlight filtered through its air, this is the question that astrobiology is building toward. The answer involves what are called biosignatures, chemical signatures in the atmosphere that could only be produced or maintained by biological processes. Oxygen is the obvious one. Oxygen is reactive. It combines with other materials. It is consumed by geological processes without a continuous biological source. To replenish it, the oxygen in Earth's atmosphere would disappear in about 4 million years. Without photosynthesis, an atmosphere rich in oxygen is an atmosphere being actively maintained by something photosynthesizing or something like it. If we detect oxygen in the atmosphere of a distant world, it would be a powerful suggestion of biology, not proof. There are abiotic ways to produce oxygen, photolysis, the breakdown of water vapor by UV radiation, can produce oxygen without biology, but in combination with other biosignatures, methane and nitrous oxide, and the specific ratios of atmospheric gases that biology produces and maintains, the case for life could become compelling, not certain, not proven, but compelling. The James Webb Space Telescope has already detected carbon dioxide in the atmosphere of WASP 39b. The first atmospheric carbon dioxide detection in an exoplanet ever, and water vapor has been detected in the atmospheres of several hot Jupiters, and sodium and potassium and helium and hydrogen. The technology is improving. Each generation of instruments more sensitive than the last. The atmospheres of smaller planets harder to detect, requiring longer observation times, more precision, more careful analysis of the signal against the noise. The signal of a habitable world is weak compared to the noise of distance and starlight and instrument noise, but it is not zero. And we are looking ocean worlds in our own solar system, the habitable places we already know. Before we go further into the exoplanetary unknown, let me bring us back closer to home because there are worlds in our own solar system that may harbor the conditions for life that we have been studying for decades and that continue to surprise us. Europa, the fourth largest moon of Jupiter, is covered in ice, a smooth, cracked, relatively feature-free shell of ice across its entire surface. And beneath that ice, a global ocean, perhaps 100 kilometers deep, kept liquid by the tidal heating, generated by Jupiter's immense gravitational field, which flexes and compresses the moon as it orbits, converting gravitational energy into heat in the rock beneath the ocean. Europa's ocean may be in contact with the rocky seafloor where hydrothermal vents could provide the chemical energy that life uses on Earth at the deep ocean vents, where entire ecosystems exist without sunlight, powered by the chemistry of hot water and rock in 1977. Oceanographers exploring the mid-ocean ridge of the Galapagos Rift in the Pacific Ocean found something that nobody had expected: hydrothermal vents, cracks in the seafloor, where superheated water, rich in dissolved minerals, poured out into the cold, deep ocean. And around these vents, in complete darkness, 2.5 kilometers below the surface, where no sunlight penetrated, life, dense, complex, extraordinary life, tube worms 3 meters long, feeding not on photosynthesis, but on chemosynthesis, using the chemical energy of hydrogen sulfide. From the vent, giant clams, white crabs, fish, shrimp, an entire ecosystem powered by heat and chemistry, not sunlight. The discovery changed everything we thought we knew about where life can exist, about what life requires. It had been assumed that sunlight was essential, that all food chains started with photosynthesis, that life was ultimately solar-powered. The deep-sea vents showed that this assumption was wrong, that life could run on chemical energy from the Earth's interior without any sunlight at all. If life can exist around deep-sea vents on Earth, then life might exist around deep-sea vents on Europa, or on Enceladus, Saturn's small icy moon that is actively venting its subsurface ocean into space through cracks in its south pole. The Cassini spacecraft, which orbited Saturn for 13 years, flew through those plumes and detected organic molecules and hydrogen and silica particles consistent with hydrothermal activity. On the ocean floor, beneath the ice, Enceladus is spraying its ocean into space for us to study without even landing, without even drilling through the ice. The ocean comes to us in a continuous fountain of water vapor and ice particles, rising from the South Pole into space and falling back or drifting away into Saturn's ring system. The E-ring, the outermost of Saturn's major rings, is made of Enceladus ocean water. We could fly a spacecraft through that ring and duster Enceladus ocean. Titan, Saturn's largest moon, is even stranger. Titan has a thick atmosphere, denser than Earth's, primarily nitrogen, with methane and other organic compounds And on Titan's surface, there are lakes and rivers and seas, not of water, of liquid methane and ethane, at temperatures of approximately minus 179 degrees Celsius, too cold for liquid water, but warm enough in the Titan context for liquid hydrocarbon. The lakes of Titan are the only stable liquid surfaces outside Earth. In the solar system, could life exist in liquid methane? Rather than liquid water, could a different chemistry, a methane-based chemistry, rather than water-based chemistry, support the kind of molecular complexity that leads to biology? We don't know. There is no theoretical reason why it couldn't. The chemistry would be different. The molecules would be different. The biology, if any existed, would be unrecognizable to us. But the laws of chemistry that govern molecular complexity don't require water. They require a liquid solvent that can dissolve molecules and allow them to interact. Water is the best solvent we know, but it is not the only solvent. And in the cold, methane-soaked, orange haze world of Titan, something might have found a different way. The Fermi paradox. Why is the universe so quiet? I have been describing a universe full of worlds, full of potentially habitable conditions, full of the ingredients and the environments that we associate with the origin of life. And yet, the universe is quiet. We have been listening for deliberate radio transmissions from technological civilizations. Since 1960, when Frank Drake pointed the radio telescope at two nearby sun-like stars and listened in what he called Project Ozma, the first deliberate search for extraterrestrial intelligence. We have been listening in various programs with various instruments at various frequencies for more than 60 years, and we have heard nothing unambiguous, nothing confirmed, nothing that has held up under scrutiny as a genuine signal from a technological civilization in a universe that is 400 billion stars large, in a galaxy that has been forming stars for 10 billion years. We have heard nothing. This is the Fermi paradox, named after the physicist Enrico Fermi, who supposedly asked at a lunch conversation in 1950, given the size of the universe and the age of the universe and the apparent abundance of suitable worlds, where is everybody? The answers to the Fermi paradox are many, and none of them is entirely satisfying. The first answer is the simplest. We haven't looked hard enough, long enough, carefully enough at the right frequencies, in the right directions. The electromagnetic spectrum is vast. The sky is large. The distances are enormous. Perhaps we are simply missing the signal, not because it isn't there, but because we haven't pointed the right instrument at the right star at the right time. This is possible, even likely, given how little of the parameter space we have actually searched. The second answer is the great filter, the idea that between the origin of life and the development of a spacefaring, communicating civilization, there is some step or some combination of steps that is extraordinarily difficult, that almost nothing makes it through. A filter through which most life does not pass. The filter might be the origin of life itself, the step from chemistry to biology, from molecules to cells, from the chemical precursors to the first self-replicating system might be so improbable, so unlikely, that in the entire observable universe, with its hundreds of billions of galaxies and hundreds of billions of stars per galaxy, it has happened. Only rarely, perhaps once, perhaps a handful of times. Or the filter might be the origin of complex cells, the eukaryotes, the step from simple bacteria-like cells to the complex cells with nuclei and mitochondria that all complex life is made of. This step happened only once on Earth, 2 billion years ago, and took roughly 1 billion years of life existing as simple bacteria before it happened. Perhaps this step is the bottleneck, the step that almost everything fails, or the filter might be still ahead of us. Perhaps the reason we don't hear from civilizations is that civilizations don't survive long enough to be heard from. Perhaps every civilization that develops technology eventually uses that technology to destroy itself. Nuclear weapons, or climate change, or engineered pathogens, or artificial intelligence, or some combination of civilizational failures that prevent the transition from a young, fragile, technologically capable civilization to an old, stable, interstellar civilization. If this is the filter, if this is what lies ahead, then the silence of the universe is not reassuring. It is a warning. I don't have a resolution to the Fermi paradox. Nobody does. The honest answer is, we don't know. We don't know why the universe is quiet. We don't know whether we are alone or surrounded by civilizations that for some reason we cannot detect. We don't know whether the absence of a signal is evidence of absence of civilizations, or simply evidence of our own limited detection capability and limited search history. The Fermi paradox is one of the deepest and most unsettling questions in science, because its answer matters enormously for how we understand our place in the universe. The search, what we are doing right now, the search for life beyond Earth, is the most ambitious and most important scientific project in human history. This is not hyperbole. If we find evidence of life, even microbial life, even the chemical signature of a biosphere on a world around another star, everything changes. The question, is life common in the universe? Which has profound implications for how we understand our own existence, our own significance, our own place in the cosmic story. Would have an answer, not a complete answer, not proof of anything about intelligence or civilization or consciousness, but a beginning, a first data point beyond the one we already have. The James Webb Space Telescope is the current frontier. Its unprecedented sensitivity in the infrared, its ability to study planetary atmospheres through transmission spectroscopy makes it capable, in principle, of detecting biosignatures in the atmospheres of rocky, habitable zone planets around nearby stars, the TRAPPIST-1 planets, the Proxima Centauri b. The other nearby candidates that orbit within a few dozen light years are within the observational reach of Webb. Not easy, not guaranteed, but possible. With enough observing time, with enough photons collected from enough transit events, the signal of a potentially habitable world might emerge from the noise. The next generation of space telescopes in planning or in development will be even more capable. The LIFE mission, our European concept for a space interferometer, multiple telescopes flying information, working together to achieve the resolution and sensitivity to directly image rocky planets around nearby stars and study their atmospheres in detail. The Habitable Worlds Observatory, an American concept for a large optical telescope specifically designed to study habitable zone planets around sun-like stars. Both of these missions, if funded, if built, if launched, would transform our ability to characterize potentially habitable worlds, to look at them not as shadows in starlight, but as distinct points of light separated from the stars, with spectra that we can analyze for the signatures of oceans and atmospheres, and perhaps biology. In the meantime, there is the Breakthrough Listen program, the most comprehensive and best funded search for extraterrestrial intelligence in history, listening with some of the world's largest radio telescopes at frequencies across the radio spectrum for deliberate signals from technological civilizations. It has found nothing confirmed, but it has searched more deeply and more comprehensively than any previous program, and it continues. And there is the optical SETI, the search for laser pulses or other optical signals from civilizations that might communicate with light rather than radio. And there is the technosignature search, looking for signs, not just of radio transmissions, but of industrial activity, heat signatures, chemical pollution, megastructure, any sign that something somewhere is doing what we do, building things, changing things, leaving marks on the universe, the deepest planets at the edge of what we can see, the furthest exoplanets we have detected are thousands of light years away, some found by gravitational microlensing, the bending of starlight by the gravity of a planet as the planet passes in front of a more distant star. From our perspective, a brief brightening of the background star that encodes in the mathematics of the light curve the mass of the lensing planet and its distance. Gravitational microlensing can detect planets at distance that transit photometry and radial velocity cannot reach, thousands of light years into the galaxy. And what it finds are the planets everywhere, around every kind of star, in every kind of orbit. The galaxy is not a rare place. For planets, it is saturated with them. The Nancy Grace Roman Space Telescope, when it launches in the mid-2020s, will conduct a gravitational microlensing survey of the galactic bulge, the dense central region of the Milky Way, and it is expected to find tens of thousands of new exoplanets, including, for the first time, a statistically significant sample of planets in the wide outer orbits around their stars, where the transit method and the radial velocity method are largely blind. The complete demographic picture of planetary systems in our galaxy will begin to emerge, and with it, a clearer understanding of how common or uncommon our own solar system is, how common are the conditions that allowed Earth to form as it did, with its specific size and orbit and chemistry and history, what we are made of, the cosmic origin of the atoms in your body. Every atom in your body was made in a star. This is one of the most frequently repeated, most genuinely profound facts in science. But it is worth saying again, in the context of exoplanets and the diversity of worlds and the question of life, the hydrogen in your body is primordial, made in the Big Bang 13.8 billion years ago, in the first few minutes of the universe's existence, when the temperature was high enough for protons and neutrons to fuse into light nuclei. The hydrogen that is part of every water molecule in your cells has been in the universe since nearly the beginning. The carbon, the backbone of every organic molecule, of every protein, of your DNA, was made in the cores of massive stars in the triple alpha process, 3 helium nuclei fusing into 1 carbon nucleus at temperatures of hundreds of millions of degrees in the nuclear furnace of a stellar interior, the oxygen you breathe made in the next stage of stellar nucleosynthesis, the iron in your blood made in the final moments of a dying massive star as it burned through ever heavier elements until the iron core could no longer sustain fusion, and the star collapsed and exploded, scattering its contents into the interstellar medium, the calcium in your bones, the nitrogen in your DNA, the sulfur in your proteins, the phosphorus in your cell membranes, all of it forged in stellar interiors over billions of years of stellar evolution and scattered in stellar explosions into the galaxy, where it drifted in molecular clouds and collapsed into new stars and new planetary systems, and was incorporated into the chemistry of new worlds, and eventually into biology, and eventually into you. When you look at the star, you are looking at a forge, a furnace that is making or has made the atoms, that everything is built from the atoms of your body were in different stars before the sun formed. Were in the interstellar medium for billions of years, were in the solar nebula that collapsed to form. The sun and planets were in the early Earth for 4.5 billion years, were in the ocean and in organisms for most of that time, were in everything that lived before you, and are temporarily for a few decades in you before returning to the cycle. The planets around other stars are made of the same atoms, the same elements, forged in the same way, by the same stellar processes in the universe, with the same physics and the same chemistry everywhere. If life arose on Earth from these atoms in these conditions, then the same atoms in similar conditions on any of the billions of potentially habitable worlds in the galaxy might produce the same result or a different result, but the result, not nothing, the final planets, the worlds at the end of time. Let me take you to the future, the deep future, the future that is hard to imagine because it is so distant from now that the present seems insignificant. By comparison, the sun is about 5 billion years left on the main sequence, 5 billion years of burning hydrogen in its core before it runs out and expands into a red giant and swallows Mercury and Venus and perhaps Earth, if Earth has not been pushed to our Vita orbit by the gentle expansion of the sun's mass loss in the later stages of stellar evolution. 5 billion years is enough time for life to have originated on Earth, perhaps 3 times over, from scratch, an inconceivable amount of time during which the planets will continue largely unchanged in their orbits, warmed by a gradually brightening sun, until the sun's expansion changes everything. After the sun becomes a red giant, after it sheds its outer layers in what is called a planetary nebula, a glowing shell of gas, illuminated by the hot core, that is all that remains. The white dwarf, a hot Earth-sized, incredibly dense remnant that will cool over billions of years into a cold, dark, black dwarf. The planets of our solar system, whatever survives the red giant phase, will continue to orbit the cooling remnant of our star in a darkening, cooling solar system for trillions of years. And in other solar systems, the same thing is happening or will happen or has already happened. Some of the stars that have already died, that have already expanded and shed their outer layers and contracted into white dwarfs, still have planets. We have found them. Planets orbiting white dwarfs, rocky planets with orbits that survived the red giant phase, intact or reformed from the debris of the expansion, cold worlds, orbiting a cooling cinder in the dark long after their star's life has effectively ended, and beyond white dwarfs in the far future, when the universe is trillions of years old rather than billions, when the stars of the current era have mostly died, when the star-forming regions have been depleted of gas, when the last main sequence stars are the red dwarfs still burning slowly, the rogue planets will still be drifting through the dark, the same rogue planets that were ejected from their systems billions or trillions of years earlier, still there, still drifting in the cold between the dying stars, perhaps still, in some of them, the heat of formation pressing against the ice, keeping a buried ocean, liquid in the dark, in the cold, at the end of the universe's active era, a subsurface ocean on a rogue planet in a universe with almost no stars, still liquid, still warm, still possibly alive. The return, coming back from the edge, we have been a long way tonight, from the glass rain of HD 189733b to the diamond mantle of 55 Cancri to the dark world that absorbs nearly all the light that touches it, to the double sun world of Kepler-Altup, to the pulsar planets orbiting the dead core of an exploded star, to the rogue worlds drifting in the dark, to the TRAPPIST-1 system with its 7 Earth-sized worlds, to the oceans of Europa and Enceladus, to the methane lakes of Titan, to the future when the stars go out and the rogue planets drift in the cold, and perhaps something still lives beneath the ice. That is a long journey for a single night, for a single quiet hour before sleep. And I want to take a moment before we drift off to sit with what we've done, what it means to make this journey in the mind without leaving the room, without moving from wherever you are lying. Right now, the human mind is the only thing we know of that can do this, that can leave the room in imagination and travel to worlds 63 light years away and picture the glass rain and feel something about it. Something that doesn't have a precise name, but that is real. A mixture of wonder and vertigo, and something like gratitude for being in a universe so strange and full, and for being the kind of thing that can notice that it is we are the universe looking at itself. This is the phrase that people come back to again and again, because it is the only phrasing that comes close to the strangeness of what we are, the atoms that were in stars. Arenus are looking at stars, are wondering about the planets around stars, are building telescopes to study those planets, are lying awake at night thinking about glass rain and diamond mantles and rogue worlds drifting in the dark, the universe, after 13.8 billion years of expanding and cooling and forming stars and forming galaxies and forming planetary systems, and in at least one of those systems producing chemistry. That became biology, that became consciousness, that became the capacity to look back at the universe and wonder about it. That is what you are right now, the universe wondering about itself. The sleep sequence, the slow drift toward quiet, let the glass rain fall, far away on a world you will never visit, in a system you cannot reach in a lifetime or 10 lifetimes or 10,000 lifetimes. Let it fall sideways at 8,000 kilometers per hour in temperatures that would be instantly fatal without your presence there, without any presence at all. The rain falls as it has fallen for billions of years before you knew it existed, as it will fall for billions more. After you have forgotten this night, the diamond mantle of 55 Cancri pressing down on its molten core 40 light years away, the carbon under pressure, forming its crystalline structure, atom by atom, in the crushing interior of a world you will never see. It is there right now, as it has always been, as it will always be. The diamond does not know you exist, and you exist. Knowing it is there, the dark planet, Strangest, moving through its orbit 750 light years away, absorbing the light that falls on it. giving almost nothing back. A massive, real, profound thing, moving through the dark, nearly invisible, nearly indistinguishable from the darkness around it, and yet there, fully, completely there, the rogue planet, somewhere in the dark, between the stars, drifting without destination, without a sun to orbit, without anything to pull it in any direction, moving at whatever velocity it had when it was ejected from its home system millions or billions of years ago, and beneath its ice, perhaps water, liquid, warmed by the heat of the planet's own interior, in the dark, between the stars, the TRAPPIST, one system, 40 light years away, 7 worlds orbiting a small red star that you cannot see from where you are without a telescope, 3 of them in the habitable zone, their surfaces unknown, their atmospheres uncertain, their potential for life unresolved, but they're real 3 Earth-sized worlds, 40 light years away, moving in their orbits around their quiet Jing Riad star. The light that left those worlds 40 years ago is arriving at Earth. Right now, as you breathe, the light that is leaving those worlds right now will arrive at Earth in 40 years, long after tonight, long after this particular night has dissolved into memory and then into something even less. The light is already traveling toward us. Breathe the way the universe breathes, in the slow exchange of energy between stars and space, between light and dark, between the forming and the dying of worlds, in long, patient, deep, as if time doesn't matter, as if time, in the context of billions of years, doesn't matter, which it doesn't, not really, not in the grand cosmological sense, only in the personal sense, and the personal sense is the only sense that feels like anything, and out, releasing whatever the day was, whatever it cost, whatever it required, let it go, the way a planet blows his mass in the solar wind, slowly, continuously, without noticing you are on a planet, a small, rocky, water-covered, atmosphere-wrapped, single-star orbiting, unremarkable, extraordinary planet, moving at 30 kilometers per second around the sun that is moving at 220 kilometers per second around the center of a galaxy that is moving at approximately 630 kilometers per second. Relative to the cosmic microwave background, you are in constant motion at all times, in every direction, at multiple scales, and yet you feel still, because all motion is relative, and relative to the surface. You are lying on, you are still. The weird planets are still out there. The glass rain, the diamond, the darkness, the rogue worlds, the double suns, the pulsar planets, built from the ashes of a dead star, all of it still there, still moving, still obeying. The physics that governs everything, everywhere, in the universe, without exception, without error, without deviation, the same physics that governs the rising and falling of your chest. Right now, the universe is full, not empty, not cold, not indifferent in the sense of being empty, full with worlds, with chemistry, with the ongoing patient, continuous process of matter arranging itself into forms of increasing complexity, including on at least one world, into forms aware of the process, wondering about it, lying awake in the dark, thinking about the glass rain on a world they will never visit. Sleep now. The James Webb Space Telescope is in its orbit, 1.5 million kilometers from Earth. Its golden mirrors, cooled to minus 233 degrees Celsius, more than 40 degrees colder than the average temperature of deep space in the infrared darkness, collecting photons from worlds that have never been seen in detail before. It doesn't rest. It doesn't need to. It is doing what it was built to do, looking while you sleep. Sleep now. The rogue planet is drifting between the stars as it has drifted for millions of years, not going anywhere. In particular, just moving through the dark, carrying whatever it carries, whatever chemistry, whatever heat, whatever buried ocean might or might not be there in the cold. Sleep now. The pulsar PSER B1227 plus 12 is spinning 161 times per second. Its radio beams sweeping through space like the beam of a lighthouse. In Anu-Chen, with no ships, no one to receive the signal except the instruments that we have built and pointed in its direction to listen and to infer from the mathematics of its timing the presence of worlds around it, real worlds built from the ashes of the explosion that ended the star, that left the pulsar that spins 161 times per second in the dark. Sleep now. The glass rain is falling sideways on HD Dub 233B at 8,000 kilometers per hour in temperatures over 1,000 degrees on a world that looks from a distance almost like Earth, almost blue, almost home, until you get closer and the glass rain begins and the wind that has been blowing for billions of years carries everything away. Sleep. The universe does not need your attention to continue. It will continue regardless. The glass rain will fall. The diamond will press. The pulsar will spin. The rogue planet will drift. The TRAPPIST one worlds will orbit. Their quiet red star, all of it, continuing while you sleep, while you rest, while the atoms that were in stars before the sun was born will rest in you for a few hours before tomorrow. The universe is old and you are brief, and that is not sad. That is the deal, the extraordinary deal that life makes with physics, a short time of extraordinary awareness, of connection to the whole in exchange for the atoms. When the time is done, the atoms return to the cycle, and the awareness, whatever it was, is released into whatever comes after awareness. For now, the awareness is here, in this room, in this body, breathing on a small, rocky, water-covered, extraordinary planet orbiting one star in the galaxy, full of worlds, and the awareness is right now nearly asleep, and the glass rain falls in the dark between the stars